Now that we've discussed the intuition behind hypothesis testing, let's look at some examples in part 2 of this lecture. We'll look at two examples. The first looks at the difference in mean education between the population from which the General Social Survey is drawn and the entire U.S. adult population. And so recall that the General Social Survey was a sample of people who are English-speaking, non-institutionalized adults. And the question is, are they going to have a different education than all Americans? That is, those that include adults who may be in institutions or who are not English-speaking. And so suppose that we had some data from the 2012 General Social Survey from a sample of 1,972 cases. And suppose that we figured out that they had a sample mean education of 13.53 years. Or in other words, let's say that Y bar represents their sample mean, and that equals 13.53. To represent the entire U.S. adult population, suppose that we had some data from the 2010 U.S. Census, and suppose that we limited our analysis to only those who are 18 years or older to make it more comparable to that we get from the census. And so let's say that we found out that on average, they had a average education of 13.2 years. Let's call that mu sub x. And let's suppose that the population standard deviation of years of education was 2.87. So how do we explain the difference between the sample mean education for the GSS respondents and what we got from the census indicating the entire U.S. adult population's education? Is it really possible that the GSS population is more educated than the national average? Or is this sample mean just unusually high? Well, we don't know a priori, and so we have to use hypothesis testing to figure it out. And so we have to use the steps in hypothesis testing. So step one is to state our assumptions. And so we make three assumptions. The first is about the level of measurement of the variable. And in this case, we assume that education is measured on an interval ratio level. The second is about the sampling procedure used. And so here we assume that we have a simple random sample from the General Social Survey. And third, we have to make some kind of assumption about the sampling distribution and its shape. And since we have a large sample size, we know, based on the central limit theorem, that it follows a normal distribution. Okay, the second step is to state our research and null hypotheses, and we have to state our alpha level. And so we'll use mu sub y to represent the unknown population parameter, that is, the unknown average education from the population from which the GSS sample was drawn. And we'll call that mu sub y. And we're going to state our null and research hypothesis. Our research hypothesis, h sub 1, is that that value is greater than 13.2. And recall that 13.2 is the census number that we got that represents the average education of the adult population. And then h naught, our null hypothesis, is that the population mean, mu sub y, for the population from which the GSS was drawn, and the entire adult U.S. population in the census are the same, and they're equal to 13.2. And so notice again that h sub 0 always takes the same form. It always says that the unknown population parameter is equal to some unknown value, or some value that we're assuming. Okay, now we have to also state our alpha level. And so we'll use a conventional alpha of 0.05. And recall that alpha is basically the cutoff between what we think is a suitable difference between what's likely and what's unlikely. And so we're basically saying here that if we find a sample result that is different from the assumed value of the population result, and it occurs 5% of the time or less, then we can reject the null hypothesis in favor of the research hypothesis. If we're finding something that occurs more than 5% of the time, we have no evidence to reject the null hypothesis. Okay, now we have to choose a sampling distribution. And remember, the basis on which we choose a sampling distribution is whether the population standard deviation is given or not. And so in this question, we had the population standard deviation given from the census data. So we don't need to estimate it. That means we don't need to use the t-distribution. We can use the standard normal distribution. So we're going to choose the z-score over a t-score when we're calculating our test statistic. And that means that our sampling distribution is going to be the one that is used with the standard normal distribution. And so here is the sampling distributions of the mean under the null hypothesis. So notice that the distribution follows a normal distribution, which is what we assume based on the central limit theorem. Notice that it's centered around what we think is the true population mean, and under the null hypothesis, we think that the mean for the population from which the GSS sample is drawn is the same as that of the entire adult population that we got from the census, or in other words, it's equal to 13.20. And then remember that we have a sample mean of 13.53. So now the question is, how far apart are these two values expressed in terms of z-scores? They seem like they're close together, but we also have to take into account the amount of variation across samples using the standard error estimate. Okay, so we're going to use this formula to calculate our test statistic. And again, it just tells us to take the difference between the sample mean, y bar, and the population mean, mu sub y, and divide it by the standard error of the mean, which is equal to sigma sub y divided by the square root of n. And so for our example, here are the numbers that we're going to use. And so recall that our sample mean is 13.53. This is the thing that we got from the census data. I'm sorry, the GSS data. Our population mean is 13.20, and this is what we got from the census data. We also got the population standard deviation from the census data. It's 2.87. And then we had a sample from the GSS of 1,972 cases. And so when we do the arithmetic, we find out that we get a value of 5.11, and that tells us that the sample mean, 13.53, is over 5 standard deviations from what we think is the true population mean, 13.2, under the null hypothesis. And so if we were to illustrate that using a figure, it would look something like this. Our z-score, 5.11, is over 5 standard errors away from the assumed value of the mean, 13.12, which we got from the census. And so now that we have our z-score, which is also known as a test statistic, we have to find something called the p-value. And so the p-value will basically tell us how likely is it that we get some sample result that in this case is over 5 standard deviations or standard errors above the mean. And so to find that value, we're going to have to look up our z-score in the standard normal table under column C, which tells us the area beyond the z-score. And this will tell us the likelihood of finding this sample result under the null hypothesis. And so here's a portion of the standard normal table. We're going to look at column C, and we're going to try to figure out which value in column C corresponds to our test statistic, 5.11. Well, notice that our z-score isn't even listed. It's so large, it's larger than the largest z-score that's listed on the table. So as an approximation, we can just use the value in column C corresponding to the largest z-score, 4 in this case. And so we don't know exactly what that value is going to be, but we know that that p-value is going to be even smaller than the smallest one listed in the table. So we know our p-value is going to be less than 0.0001, or in other words, only fewer than 1 in 10,000 samples have this result by chance alone. And so to illustrate that, this figure basically shows not only the location of our test statistic, but its probability value, the p-value. And so we can see that not only is it 5 standard deviations above the mean, but the chance of finding something like that by chance alone is less than 1 in 10,000. And so our p-value here is less than 0.0001, a very unlikely result. And so step 5 involves making a decision. So here we're going to compare our p-value to our alpha level. So remember, the difference between these two is that the p-value is the probability of getting our actual sample result under the null hypothesis, which in this case happens less than 1 in 10,000 times. And our alpha level is the cutoff between what we think is sufficiently unlikely to reject the null hypothesis. And we said that we're using a value of 0.05. So if we find that our sample result happens less than 5% of the time, we can reject the null hypothesis. And in fact, that's what we find in this case. So here our p-value is less than our alpha level, and so we can reject the null hypothesis. And so that means that this sample result less than what we think is sufficiently unlikely. And so it seems that the null hypothesis is unlikely to be true. Another way to do this test is to compare the test statistic directly with something called a critical value under the rejection region. And so the critical value is basically a z-score corresponding to the area under the curve defined by our rejection region. And so to find the critical value, what we have to do is we have to take our alpha level, 0.05, and the fact that we have a one-tailed test, and we have to figure out what z-score corresponds to that area under the normal curve. And so here's an illustration of our rejection region. So notice that this test is going to be completely evaluated in the right tail of the distribution. Why is that? Well, because recall our research hypothesis was that the value was greater than some value. And so we're going to be doing a right-tailed test, and it's going to be evaluated entirely in the right tail of the distribution. And so you can see that an area in the right tail of the distribution of 5% defines our rejection region. And so what we're looking for is a critical value that includes 5% of the area under the normal curve. And so if we look that value up in column C of the table, we're going to try to figure out which z-score is the first to include a value of 0.05. And so we can see that the first one to include 0.05, or something very close to it, is 1.65, and that's our z-score. So our critical value in this case is 1.65. And so we can compare our critical value directly to our test statistic. And so this picture basically illustrates that idea. And so notice that our test statistic is very far away from our critical value. It's well within the rejection region. So in this case, our test statistic is larger than the critical value, and the test statistic is well within the rejection region, or the area under the curve that we said we can reject the null hypothesis. And so since our critical value is less than our test statistic, or put differently, if our test statistic is bigger than the critical value, 5.11 is bigger than 1.65, we can reject the null hypothesis. And so since we reject the null hypothesis that the average earnings for the GSS population is equal to that of all adult Americans, we have more evidence for our research hypothesis that actually the population from whence the GSS was drawn has a higher education on average than the US population. Okay, as a second example, consider this same example, but this time suppose that the population variance wasn't known. Let's say it wasn't given to us. And so suppose we wanted to know in this case whether the education from which the GSS population, from which the GSS sample was drawn, was different from, on average, the entire US population. So again, suppose this time we weren't given the value of sigma. Suppose it was unknown. So suppose we had the following scenario. Suppose again we took data from the 2012 General Social Survey, a sample of 1,972 cases. Suppose that our sample mean again was 13.53 years of education, but suppose this time we had a sample standard deviation of 3.13 years. And suppose that from the census data, we only got the information on the average education, but not the population standard deviation. And so let's say this time all we know is mu sub x is 13.20 years. Okay. Notice that again, the GSS sample seems to have a larger average education than the entire US population based on census data. So is that indicative of the fact that the GSS population is more educated, or is this GSS sample data unusual? Well, we have to use hypothesis testing again to determine that. And so step one is to state our assumptions. So they don't change very much. Again, we assume that there's a random sample from the GSS. We assume that education is an interval ratio variable. And again, we have a large sample size. And so we don't need to make any assumptions about the distribution of the sampling distribution. We know based on the central limit theorem that it's normally distributed. Only in the case of a small sample that is less than 50 cases do we need to assume that the sampling distribution is normally distributed. And that assumption is motivated by the fact that education in the population itself would have to be normally distributed. Okay, so step two involves stating our hypotheses and stating our alpha level. So there is one change this time. This time, since we're not specifying a direction in our research hypothesis H sub 1 is that mu sub y, which again represents the population education from which the GSS sample is drawn, is not equal to 13.2. And our null hypothesis is the same as it was last time, that it is equal to 13.2. And again, we'll use the same conventional alpha level, 0.05. Okay, now we have to choose a sampling distribution. And unlike last time, we're not given the value of the true population standard deviation. And we have to estimate it with the sample standard deviation. And so this time, we're introducing more sampling variation that's not taken into account properly by the standard normal distribution. And so we have to use the t-score instead of the z-score, because that correctly takes into account that additional sampling error. And so the formula for our test statistic now will be a t-value, which is going to be equal to, again, the difference between the sample mean, y bar, the true population mean, mu sub y, and this time the estimated standard error of the mean, s sub y divided by the square root of n. And this statistic follows a t-distribution with n minus 1 degrees of freedom. And so we'll calculate our test statistic very much the same way that we did last time. We'll take our sample mean 13.52 from the GSS data. We'll subtract 13.2, which is the assumed value of the population mean under the null hypothesis that we originally got from the census data. We use the sample standard deviation we got from the GSS data this time, 13.17, and we'll divide that by the square root of the sample size, 1,972. And then we have to figure out our degrees of freedom by taking the number of cases, 1,972, and subtracting 1, leaving us with 1,971 cases. And so this time, when we do the arithmetic, we get a test statistic, or t-value, of 4.68. And so that tells us that this sample mean is over 4 standard deviations above the mean, a pretty far distance. Okay, so under the null hypothesis, we have a sample mean that's over 4 standard deviations from the population mean, or the assumed value of the population mean under the null hypothesis. Does that seem likely? Well, unfortunately, it's hard to tell what the p-value is, because the t-table isn't as detailed as the standard normal table. So rather than using the p-value, what we'll do is we'll compare our test statistic directly to the critical value that we'll get from the t-table. So let's just see how we do that. So step 5 involves making a decision. So we're going to use the t-table. We're going to find our critical value corresponding to a 0.05 alpha level, 1,971 degrees of freedom, and a two-tailed test. Remember, we're using a two-tailed test because our research hypothesis is non-directional. So the next slide basically shows you how to find the critical value from the t-table, meeting those conditions. Okay, so here's our rejection region. We see that we have to split it in half. Half of it goes in the left tail of the distribution, half of it is in the right tail of the distribution. And that's because, again, we have a non-directional research hypothesis. And so at a 0.05 alpha level, half of that area is in the left tail, half of it's in the right tail. Let's look at the t-table to find our critical value. And so we have 1,971 degrees of freedom, which is equal to the number of cases minus 1. But that's not listed. And so we'll just use the last column of the table, the infinity column. Now we have to find our alpha level, and whether we have a one-tail or two-tail test. And so recall that we have a two-tailed test because we have a non-directional hypothesis. And we have a 0.05 alpha level. And so it turns out that our critical value is 1.96. And so we're going to compare our critical value, 1.96, to our test statistic, 4.68. And we're going to reject the null hypothesis because our test statistic is greater than our critical value. And so we conclude that the mean of education is different across the GSS population and the entire adult population.